Okay, entropy. So entropy, these two vectors will connect these two, energy. So entropy we already learned in chapter 6. What is the symbol for entropy? The symbol. X, Y, Z, A, B, C, what is it? H, right? It's an H, entropy, okay? We use H to represent for entropy. And then we have entropy change. You have a reaction, then you have your reactants product. So there will always be entropy change. We use delta, right? Anything change, we use delta to represent for the change. So it's delta H. So H means entropy. This entropy change, we use delta H to represent for that. And we also have a unit for the entropy or entropy change. They are the same unit. Usually we use kilojoule because it's an energy, right? Kilojoule per mole. Sometimes you can use a joule per mole. You can always do the conversion. But in most cases, we use kilojoule because usually the H or delta H is a large number. Okay, so that is the entropy and entropy change. So then, if you still remember, actually we mentioned a lot of times, right? If you have delta H, entropy change, positive or negative, we define this as a different process. If it's positive, what kind of process?
Endo.
We use endo or exo, right? So positive means gain energy, gain heat, you absorb heat. So it's endo. Come here, right? Come here, endo. If it's negative, means you release heat, you're losing heat, so become outside, called exo. Again, this we are talking about the system, right? If the system is the endo, means the surrounding provide heat, right? So the system lose heat, release to the surrounding. Okay? So it's we are focusing on our system. So that is from the entropy change. Okay. So through the entropy change, delta H, we can only tell the system is gaining heat or losing heat. However, you cannot determine the system is a spontaneous process or non-spontaneous process. Look at it here. So here is that, okay, most spontaneous process proceed from the system with higher entropy to the system with lower entropy, which means for the exothermic, right? We can say most exothermic process are spontaneous. But there are some spontaneous process proceed from a system with lower entropy to a higher entropy direction. That means some endothermic process can also be spontaneous, which means you cannot use this endo or exothermic process to determine is it spontaneous or not. So we cannot use delta H to determine the spontaneity of the process. You cannot. Then we introduce another term called entropy. Okay, so entropy is the factor that can tell you the spontaneity. Okay, it's also a type of energy, but it tells you whether the process is spontaneous or not. Okay, entropy cannot tell you, but entropy can. So what is entropy? This is a new term we will start it. Okay, so entropy, we use a symbol S to represent for that. Okay, we use entropy. So what entropy tells you? Entropy tells you energy, right? So entropy is also the energy, but it tells you the randomness. The randomness of the system. Whether it's very organized, the molecules are very organized, or it's no order at all, it's moving everywhere, right? So that randomness of the system, we use entropy to define that of the system. Okay, the system. So the more randomness your system, the higher entropy you will get, or the more entropy you will get. Okay? So for example, if you have ice compared with liquid water, so which one will give you a higher entropy? Liquid water, right? Because we know ice is more organized, and the water liquid, the molecules are more random. So how about liquid water compared with gas water, Steve? Gas, right? So gas, because they are very far away from each other, they move a lot, so it's more random. So that tells you, okay, for example, my solid has an entropy smaller than liquid, smaller than gas. Okay, so that is the opposite order as your intermolecular force. Okay? So then we have entropy change, similar as entropy change. So entropy change, you can use delta S. Right? So entropy change, for something change, we always use delta. And both the entropy and entropy change have the same unit. It's joule per mole per K. Okay, so that is the unit for entropy. So keep in mind, entropy we have kilojoule, but entropy we always use joules because it's usually a smaller number. Okay? So if it is for a reaction or any process, the same concept, same definition as entropy. Right? It's always your S final minus your S initial. It's the difference between your final state and your initial state. So here, actually, same thing for your delta H. Right? I did it right here. Right? Same thing for your delta H. Delta H also always equal to your H final minus H initial. Always the same thing. Delta means the difference between final and initial states. Okay? That is. So now there are some factors affect entropy. First factor always temperature. Because why solid ice convert to liquid water? To heat it, right? You can heat, so temperature is a factor. Temperature. In general, we say the higher the temperature, the higher entropy you will get. The temperature increase, the entropy will increase. Okay, it's a positive relationship. And second factor is the state of your substance. That is what I give you here. Okay, so we have gas larger than liquid, larger than solid. Because gas is more random. So that is dependent on the state. And the third one, we talk about if it is a reaction. Okay, so for reaction, for chemical reaction, the more gas you have, the higher entropy. So actually it's related with the second factor, right? So gas gives you higher entropy. So if you have a reaction involved in gas, so you have to compare which side gets more gas. The more gas, the higher entropy. So we will see some examples, right? So number 1 and 2, we already did some example. Now let's see another example. For example, here, if you have this reaction, gas, 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 they are all involving gas. So now let's see. I ask you the delta S, the entropy change for this reaction will be positive or negative? So first, delta S equal to S final minus S initial, right? Initial. So S final means everything. So S final you get 2 sulfur dioxide and 1 oxygen. So they are both gas. So 2 plus 1, you get 3 gas, right? 3 gas. So in the beginning of reaction, you get 2 gas. So which side gets more gas? Product, right? Eventually you get more gas. So more gas means more random, means higher entropy. So your delta S here should be positive. Okay? That's very important to know it's positive. Because we're going to have a conclusion here. If you get a positive delta S, which means delta S is larger than 0, right? Positive. So the system or the reaction, sometimes it's a process, is spontaneous. Okay? We can use entropy change to define the spontaneity. If it's positive, it's a spontaneous process. We cannot use entropy change to determine the process is spontaneous or not, but we can use entropy change. If it's a positive change, then it's a spontaneous process. In another way, if it's a negative, right? Negative, it's a non-spontaneous. Cannot go backward. Non-spontaneous. Okay. So that is the concept for entropy and why we introduce entropy, because you need to know whether this reaction can go spontaneous or not in reality, right? If it cannot, you need to do something. Okay? So spontaneous only if only if your delta S is positive. Otherwise, it's not spontaneous. Okay? So, and we know, okay, since the delta S here is a positive, that means this process, this reaction can occur spontaneously. Right? So that is some concepts and some conclusions. So now, since we already started first law of thermodynamics, we know, okay, no free lunch, energy change always zero. Will that happen the same thing to the delta S? Will the delta S universe be zero always? Answer is no. Okay, so delta S universe can be any number. It can be a positive number, can be a negative number, it can be zero. So that is different from the energy. So let's say what happened to delta S universe then. And is your second law of thermodynamics. Just use this way, second law of thermodynamics. Talk about the delta S universe. So the delta S universe, for the universe must be positive for a spontaneous process. So we already know if the process wants to be spontaneous, if for a system, right, it should be positive. Same thing for universe. If something wants to happen spontaneously, you must get a positive delta universe, delta S universe. And same definition as delta H universe. The delta S universe also equal to delta S system plus delta S surrounding. So no matter it's delta S, delta H, or later on we started delta G, we only have two parts for our universe, the system and the rest of the system. The rest of the part is called surrounding. So delta S system, delta S surrounding. So anything beyond your system is your surrounding, right? Anything else is your surrounding. So to make sure your process is spontaneous, your delta S universe should be a positive, not just the system, but the whole thing. Okay? And just further continue with the second law. So if your delta S universe, so when we started this chapter, it's very important to pay attention to the subscript. Okay, so delta S universe, if it's a positive number, then this process is spontaneous. If the delta S your universe is a negative number, and of course it's a non-spontaneous, but it can happen, it exists, right? So not as the delta E, always there, but here can be positive, can be negative, non-spontaneous. Okay? If the delta S universe, okay, so for second law, we talk about universe. If it's equal to zero, what happens? That means it can go this way. It can also go that way, both spontaneous, right? So it does exist. It's a reversible reaction. And we already know reversible reaction does exist, and it gives you equilibrium, right? So delta S universe equal to zero can occur, can exist. So all these situations are possible. Positive, negative, zero. And for you, you have to know, if it's positive means what? If it's negative means what? If zero means what? Okay, so you have to know the conclusion. So any questions so far? Lot of concepts. Okay, so now let's introduce some math. Right? Since we know, okay, delta S, delta H, a lot of things. And also we know this is an energy, delta H also energy. Is there any relationship between this? Yes. So let's see what kind of relationship between delta S and delta H. So we have to combine the first law and second law of thermodynamics. So from the, review the first law again, right? So equal to 0, so 0. And we already know this 0 is delta E system plus delta E surrounding, right? Surrounding. And usually, so I'll write one more step. System equal to negative delta E surrounding. That means we already know. And we already know that when we started a system in a certain volume. So here, just one more step, right? Delta E usually equal to Q plus W. I'll go back to review. Q means the heat. W means the work, right? If it's for the system with a fixed volume, the volume not change, so the W usually is 0 because it's equal to T pressure times delta V, right? If delta V is 0, so this W usually is 0. So that's why in most cases we just consider the heat, because when we talk about our system, usually it's a reaction. So for the reaction, the volume usually not change, okay? The total volume, I mean, they are in the same container, right? So if delta V equal to 0, so W equal to 0. So that means in most cases, delta E equal to Q. So you get this part? Why delta E equal to Q? Because no volume change, right? So delta E usually equal to Q. That means this delta E system and delta E surroundings can be written by Q. Q system equal to negative Q surrounding. Okay, so now to understand why this comes from only Q. Again, because delta V is 0, no volume change. So it's only consider Q. All energy change comes from the heat. Okay, so we already know that. And further, in most our situations, because we do heat, right? We only do heat, and the heat all comes from energy change. So that means your delta H equal to your Q. The enthalpy change equals to your heat change. Next system. So these two equal to each other. Okay? With different symbols. So now that is what we got from the first law of thermodynamics. Then we're going to define a relationship. This is defined. Delta S surrounding equal to Q surrounding over temperature. Okay? And this temperature here must have a unit Kelvin. Right? Unit Kelvin. And that is why the delta S got a unit kilojoule per mole per K. But the energy Q only have joule per mole, right? So because you use energy divided by K. And since we already know this, because usually we started the system, we don't know what happened to the surrounding, right? So we want to convert this to be our system. So Q surrounding is negative Q system. Right? Negative Q system. So over temperature. And further, because Q system is H, so we use delta H system over temperature. And this Q, we can measure through certain method. And this delta H, we can also measure or calculate. So that gives you a very common equation we use a lot is delta S surrounding. Be careful, delta S surrounding equal to negative delta H system. Don't forget this negative sign because it's surrounding, both positive, same sign. But when you convert surrounding becomes system, you have to use negative sign because it's same. Right? That is an equation we used a lot. So surrounding, actually, system. Now let's, based on this equation, let's work with the problem, right? So again, you must review chapter 6. Okay, when we started this chapter, we're going to use a lot of information from this. So now let's see. Consider this combustion. Combustion means something burned, right? Burned, okay, oxygen of the propane. And you're given delta H reaction. So is delta H reaction your delta H system or surrounding? So when you're given a reaction, we are focusing on the reaction, right? So this is your system. So this delta H reaction is your delta H system, okay? System. Remember, if you're given a reaction, that reaction is your system. System means you're focusing on that, you're starting on that, okay? So calculate the entropy change in the surroundings for this reaction at 25 degrees. Then we need the equation, right? Surrounding, temperature. So first thing, of course, you need to convert degree Celsius to become Kelvin, right? Plus 273. So now delta S surrounding equal to negative. Don't forget the negative because you're going to use your system. So here, it didn't ask you the unit, so if you use kilojoule, it's fine. So let's say negative. So negative, and delta H reaction already a negative, so you still put a negative sign here. No matter it's a positive or negative, you put whatever number it is. So here is a negative, you put your negative, okay? Temperature must be in Kelvin, so 298. Kilojoule per K, because here is not per mole, so here is per K. Okay? If here is per mole, so here is per mole per K. So that is the first question. Calculate the entropy change of surrounding. All right, I directly do this because you're given delta H. Any question for this one? Now let's say B. Determine the sign of the entropy change for the system. Can you do that? Is it positive or negative? What do you do? Depends on the state. Since it's a reaction, they're all gas. So the more gas give you more entropy, right? So delta S now is the system. Equal to S final system, right? S initial, I don't know the exact number, but I can tell based on how many gas they have. The more gas you have, the larger entropy. So let's say the product side, how many you got? 3 plus 4, you get 7. The reaction side, you get 1 plus 5, you get 6. So which side gets more gas? Product side, right? So the delta S should be positive. I don't know the number, but I know it's a positive number. Okay? Because here, after reaction, your final state, you get 7 gas. Initially, you only have 6, so it's more random. So you get positive. Okay? So now let's say determine the sign of the entropy change for the universe. Ask you if it's spontaneous or not. So what is delta S universe? Delta S surrounding plus delta S system. Delta S surrounding, I do know the number, 6.86 kilojoule per K. And delta S system, I don't know the number. But I do know it's a positive number, right? So a positive number add another positive number, so you will get a positive number or negative number? Of course positive, 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 you get positive. I don't know the exact number, and the question didn't ask you the exact number. It only asks you positive or negative. So it is a positive. So the delta S universe positive, spontaneous or non-spontaneous? Spontaneous. That is the second law of thermodynamics, right? See, related with this delta S surrounding system, sometimes you even don't need to know the exact value of it. You just need to know it's positive or negative. So it depends on the given information. Okay? Any question here? So 3 steps. If you follow the strategy, then you will be able to get it. So next, I'm going to start a little bit. Here's my Gibbs free. So at least next class, we're going to talk about Gibbs free energy. Quickly give you the definition for Gibbs free energy. Then you can go back and do the pre-study. So delta G, these are the only 2 terms we introduced for this chapter. Delta S and delta G. Delta G is called Gibbs free energy. And this is a definition equation. So we define delta G system equal to negative T temperature in Kelvin, okay? Times delta S universe. This is a very important equation, because some of you probably already know we can use delta G to determine the reaction spontaneity. But you probably don't know why. And when we started delta S universe, everything will be clear. Think about the second law for thermodynamics. We define when delta S universe is negative, it's spontaneous. So when delta S universe negative, you put a negative sign. What happens to delta G? Positive, right? That's why we say when you have delta G system, it's a positive number, so this process or reaction is spontaneous. Give you the conclusion, go back and think for that. Delta G system is negative, it's not spontaneous. Oh, sorry, wrong way. If it's positive, it's not spontaneous. If it's negative, it's spontaneous. If it's equal to 0, means reversible. And it's because of the definition. Okay, so I'm going to stop here today. So go back, really read about the delta G, and we